So generally, let's compare our SN1 and SN2 reactions. That was kind of the point of today in talking about all of the things that can affect these reactions. We talked about their rate laws. An SN1 reaction is unimolecular. So remember, its rate is controlled only by the electrophile here, the substrate. An SN2 reaction is bimolecular, and so both reactants, the substrate and the nucleophile, will control the rate because both of them are important for the slow step. What's the big barrier when we're looking at an SN1 reaction? This is going to be how stable the carbocation is. During that slow step, we're forming a full carbocation, and its ability to be stabilized will help with the reaction. It will help the rate of the reaction. And so this is the thing that we're most concerned about during an SN1 reaction is stabilizing the carbocation. In an SN2 reaction, there's no carbocation. So the barrier that you have to overcome for this reaction is any steric hindrance. That's again because this happens through a backside attack. And so you want to limit steric hindrance for an SN2 reaction. Okay, what about the electrophiles? We talked about alkyl halides as electrophiles today. Remember that we can have different types of electrophiles. And generally, the trend is that for your electrophile in an SN1 reaction, a tertiary is best because it helps stabilize the carbocation, followed by secondary, then primary being the worst. And you almost never see an SN1 reaction with a primary. Now for an SN2 reaction, again, your primary is going to be best for a methyl version, a secondary following, and then tertiary is the worst for an SN2 reaction. Here's some things to look for when kind of deciding how a reaction is going to progress. In an SN1 reaction, we actually tend to have a weak or neutral nucleophile. So something like water, for example. In an SN2 reaction, you tend to have a strong nucleophile, generally bearing a negative charge. And refer to the chart where we talked about strengths of nucleophiles, because here you'll see that something that's very strong is going to be active in an SN2 reaction more so. What to look for in solvents. SN1 reactions usually tend to have a polar protic solvent. Again, water is a good, it can act as a nucleophile, but it can also be a polar protic solvent. Or something like an alcohol, like ethanol or methanol. Remember we talked about solvation in an SN1 reaction and how having these available, your polar protic solvents available as the nucleophile helps with that SN1 reaction because now they are present everywhere. But generally something that is polar and protic, meaning it has a available proton on it. For SN2 reactions, we're actually going to see things that are still polar but aprotic. This is something with it does not have a available proton. Normally you would think of this as potentially an acidic proton on the solvent. So things like DMSO or acetone are good SN2 solvents. So again, if you see these solvents, you're usually doing an SN2 reaction. And the stereochemistry. In an SN1, remember we have a mixture occurring of both retention and inversion, but generally this can be swayed towards more or less inversion occurring. And for an SN2 reaction, you only have inversion occurring. It's 100% stereospecific. Okay, so let's do some practice. We have some questions here, and you're going to try to decide, first of all, what kind of reaction is occurring? Would it be an SN1 or SN2? And based on that, then think about which reaction would occur faster. So here I say which alkyl chloride, this is going to be our electrophile, will react faster with sodium iodide in acetone. So notice sodium iodide is a very strong nucleophile. Remember, iodine attached to a salt makes a very strong nucleophile. So first of all, we have a strong nucleophile. And second of all, our solvent is acetone, which is polar aprotic. These are signs that you're doing an SN2 reaction. In an SN2 reaction, what kind of electrophile do we want? We want one that is primary, right? And then it's going to decrease as you go to tertiary. So the best electrophile to have would be something primary. So here, if we look at our choices, we have a couple where the chlorine is bound to a carbon that is primary, which is this one or this one, A or C. This one, sorry, A and C, also these have primary bound carbons, and D does not. D has a carbon that has these additional carbon groups here and here. So now when comparing A, B, or C, remember for SN2, you want to have the least amount of steric hindrance. And in that case, we would go for our answer B. Now, even though the rest of these further down are further down away from the carbon directly attached to the chlorine, they still can cause steric hindrance in a backside attack. And so for an SN2 reaction, you want the hydrocarbon with the least amount of steric hindrance and with a primary or secondary bond. Okay, here's a similar question. Which alkyl chloride will react faster in sodium iodide with acetone? Now, these are the same setup. Sodium iodide, again, is a strong nucleophile. And we have acetone, which is polar aprotic. So this is an SN2 reaction. Now, when I look at these, again, we're going to think about our primary is better than secondary, is better than tertiary. But when I look at the carbons attached to the chlorine, another thing I notice is that these have double bonds. And one thing we talked about is that in general, our electrophile for an SN2 or an SN1 reaction has to be sp3 hybridized. That means no double bonds on the carbon that is our electrophile. So these A and C cannot be our alkyl chloride. Now, comparing B to D, it's pretty straightforward. Now we're just looking at primary, secondary, tertiary. You can see there's a lot of steric hindrance in D, and so B would be our answer. Okay, let's talk about products, how to predict products, also understanding which type of reaction you're going to be doing. So here it says, what is the major product of the reaction of a dihalide? Here's our electrophile, a dihalide that has reacted with one equivalent, this is key, one equivalent of this NaSH in dimethyl sulfoxide. So let's first discuss what type of reaction will be occurring. Notice we have the MSO as our solvent. That is another polar aprotic. And we're using a pretty strong, NaSH is a pretty strong a pretty strong nucleophile. So a strong nucleophile, which again keys us in that this is an Sn2 reaction. Now we're using one equivalent, and here again our nucleophile is NaSH. So let's think about what is going to be added on. What will be our substituted end is going to be an SH group, right? That's our nucleophile. So an SH group is going to be added somewhere on this molecule. The next thing to think about is in this molecule, this electrophile, which of these, the CH3O, the bromine, or the fluorine is a better leaving group? Which one's going to be better as an electrophile leaving group for an Sn2 reaction? So we're comparing things like the positioning. Is it a primary, secondary, or tertiary position for the leaving group? And we're also thinking about how good it acts as a leaving group, as an electrophile. Now, if you remember in the electrophile groups, things that act as better acids that are large are going to also act as our better electrophiles. In this case, fluorine does not act as a good electrophile, and neither does CH3O, this group here, leaving us with bromine as our better electrophile area. So bromine is what will be substituted, and because it's only one equivalent, that means only one substitution will occur. So we should substitute out our bromine with a thiol group. So both B and D show, our answer B is the only one that shows bromine substituted out with a thiol group. And notice that another key feature that should be present is that the thiol group is inverted. It starts as a bromine wedged forward and ends as a thiol hashed backwards. And that's again because we have Sn2 and you have inversion occurring. Now you can actually eliminate some of these other ones, again, based on the group that would be leavings. So for example, A shows our CH3O being substituted, which is not a good electrophile. C shows the fluorine being substituted, which is not a good electrophile. In fact, fluorine is a very bad electrophile. And then the problem with D is that it shows substitution of both bromine and fluorine, which we only have one equivalent here of our thiol, and that substitution cannot occur doubly if you only have one equivalent. So again, answer is B. Okay, and let's try one more question. Here we're going to try to guess the reactants based on our product. So which combination of reactants will give 1-iodobutane? Let's draw that out just so we have an idea of what it looks like. 1, 2, 3, 4. This is a butane that has 4 carbons. And we have an iodine on the 1 position. So I'm going to draw this. So again, 1, 2, 3, 4 carbons and an iodine on the 1 position. Now, this is our product, and I want you to notice that our product is a primary, has a primary carbon attached to our halide. That is the #1 clue on what type of reaction will be occurring. This has to be an Sn2 reaction because it results in something that has a primary position. An Sn1 reaction would result in something that has a secondary or tertiary position. So again, key point is that it is a primary product, and so it must have been an Sn2 reaction. So we want to pick a set of reactants that would be good for an Sn2 reaction. Okay, so if we go through, here is a butane with a HI. So this is our nucleophile and our electrophile. Now notice our electrophile doesn't have a leaving group on it. There's nothing there that can be substituted to then add the iodine on. So A is already not a good set of reactants. There's no leaving group. Okay, B has a electrophile with an OH group, this alcohol, and it has a potassium iodide. So here our leaving group would be an alcohol, and it's in the primary position, and we have a pretty strong nucleophile, potassium iodide, as our reactant as well. Now, what about our nucleophile? How does, for example, OH compare as a nucleophile? The nucleophile here is pretty weak as an alcohol, and those tend to not be good in an Sn2 reaction. Well, let's look at C. C has a very similar setup, except that we're using bromine as our electrophile here, and this is a much better electrophile. It has a much better leaving group. Sodium iodide, this is also a very strong and good nucleophile. And notice that we also have acetone, which is an aprotic solvent. This is another good thing for an Sn2 reaction. So again, we have a good electrophile, a strong nucleophile, and an aprotic solvent. These are all key for an Sn2 reaction. If we look at D, we notice immediately, #1, no leaving group, and instead it has a double bond, which we can't have on our carbon that the substitution is occurring on because it needs to be sp3 hybridized. Another key thing to eliminate this is it's in water, which is a polar aprotic or polar protic solvent, which we do not want for an Sn2 reaction. So here again, comparing B and C, the key things that are different is that B uses a polar aprotic solvent, acetone, which is good, and it has the better electrophile, bromine, when comparing. So our answer here would be C. C would result in a good Sn2 reaction, making the product that we desire. Okay, that's it for going over Sn1 and Sn2 in Chapter 6. Most of Chapter 6 is going to be exactly just based on this lecture, so really understand the intricacies of types of solvents that are good for Sn1, the stereospecificity how the rate is affected in SN1 versus SN2. Again, mostly you're going to want to look at this chart right here and really take in the comparison of our SN1 and SN2 reactions and be able to identify those and which reaction would occur, an SN1 or an SN2 reaction. Now, the other thing to go through is to really get a grasp on what is your nucleophile and what is your electrophile. Be able to identify those in a substitution reaction and know which one is a strong electrophile and which one is a weak electrophile, and which one is a strong nucleophile and which one is a weak nucleophile, because those are key again for SN1 and SN2 reactions. Okay, guys, thanks.